So, good afternoon, everyone, and welcome to today's lecture. This lecture is a continuation of what we have been doing in the last class. What we were doing in the last class?
Hmm, I,
What we were doing in the last class?
um, acceleration due to gravity and
We were dealing with, yes, very,
variations in value of g.
yes, we were dealing with the variations in the value of G. That was in the yesterday's class, and I hope we remember what we were doing, right?
Yes, sir.
We had seen we had seen two variations, variation due to shape and variation due to height, and we had noted certain points about as well. The acceleration due to gravity is the maximum on the surface, and as we go above the surface, it changes, and we had seen the formula. We had also seen the shortcut formula. The
Yes.
shortcut formula is only valid when the value of h is very, very small. Yes or no?
Yes, sir.
So now this is the new class. We will go ahead and see the third factor on which acceleration due to gravity depends on. What is the third factor on which the acceleration due to gravity depends on? Yes.
1 minute.
What is the third factor on which the acceleration due to gravity depends on? And the third factor is due to depth. Due to depth. What is the effect
Depth.
of getting under the surface of earth? If we get inside the surface of earth, what is the value of g? Yes, can anyone tell me that? Can anyone tell me the value of g inside the surface of earth? Now when we are talking about inside the surface of earth, the diagram looks like this. What is the value of g at a depth d inside the surface of earth, below the surface of earth? Yes.
Decreases, sir.
Yes, beta?
It decreases, sir.
It decreases, but what is the formula? How does it decrease? What is the relation? That is what I'm asking here. What is the relation? How do you get the value of G inside, inside, under, inside the surface of Earth? Yes? Any idea? No idea. Huh? No idea, right? What would be the value of G inside the surface of Earth?
It's 4 by 3 pi g r minus d, sir.
4 by 3 pi, yes?
4
Tell
by
me, tell
3
me.
pi g r
4
minus
by 3.
into rho. 4 by 3 pi g into r minus d into rho.
That is correct. How did you get it? That is correct. How did you get it? How did you get it? That is correct. How did you get it? Huh? Just because on the surface it is 4 by 3 pi rho into g into r. From there you have guessed that the value of g under the surface of earth will be 4 by 3 pi rho g into r minus g. Isn't it? That is how you have guessed it? Yes or no?
Yes, sir.
That is the problem. That is the problem that we don't remember. We have already seen the value of gravitational field. How does it vary inside the sphere? Inside the sphere, it is directly proportional to the distance from the center. The formula in yellow is the formula that you should have remembered, not made a formula from your own likings. That is the formula that you should have remembered. Why I am using G for gravitational field? G is same as acceleration due to gravity. In fact, gravitational field is same as acceleration due to gravity. I had already given you this formula, but you did not recall this formula. You just applied your logic, which in this case was not wrong, but that is the formula that you should have remembered. That is the formula that you should have remembered. Anyways, so inside the surface of Earth, acceleration due to gravity, which is same as the gravitational field, there is no difference at all. They are both same terms. Is directly proportional to the distance from the center of Earth. It is directly proportional to the distance from the center of Earth. There is no doubts about it because we had seen it. Now, if I call the acceleration due to gravity on the surface as gm by r square, 4 by 3 pi rho g r, then acceleration due to gravity inside the planet at a distance d from the surface can now be written in this fashion. Can now be written in this fashion. And this is same as writing it in this fashion. This is nothing but equal to gm by capital R cube multiplied by small r. That is the formula that you should have remembered. Anyways, now when you divide the two formulae, you can get the value of g dash in terms of g. G dash is equal to g into 1 minus d by r. Now, this formula is the exact formula. This is not an approximate formula. This is an exact formula and it is valid everywhere. And it is valid everywhere. Now, this formula looks similar to the formula that we had arrived for variation of g with height, this pink one. But remember, this pink formula was an approximate formula which was only valid when h was small. So this is the difference between the two formulae that we have derived. One formula, that is the formula for height, is only valid. This formula is only valid 1 minus 2h by r. This formula is only valid when the value of h is very small. But the formula for variation with depth, it is always valid because that is the right formula and we have not taken any approximation. So remember this because you might make a mistake. Once you use this formula, you might think that the other formula is also of the same type. The other formula is an approximate formula. I hope you will remember this. Yes or no? No, yes. So
Yes, sir.
remember this, that this formula that you are seeing, variation with height, is only an approximate formula and it will not be valid for value of h, which is comparable to the value of r. So this is the formula for variation of g with depth. Now you must remember certain points, important points. So now let us write those important points. Point number 1. If you go inside the surface of Earth, will the value of g increase or will the value of g decrease?
Decrease.
And you must always remember that value of g decreases because value of g is maximum on the surface of Earth. So this is pointer number 1. Important points. Important points. With depth also, the value of g decreases. In fact, you must remember the value of g is maximum gm by r square, which is on the surface of planet Earth or any other planet which is spherical in shape. Most of the planet are spherical in shape. Then you can also understand what is the value of g at the center of the earth? What will be the value of G at the center of the earth? Eh?
Is it 0, sir?
What will be the value of G at the center of earth? You can put in the
0, sir.
formula D equal to R, and otherwise also you can understand that the value of G at the center of earth is going to be 0. The value of G is also 0 at one more point. What is that point? Value of G at infinity is also equal to 0. Don't forget this.
Yes, sir.
The simple points that you must remember. Now this question as always comes, which talks about the percentage change. And you must remember, whenever you talk about percentage change, this is how G varies: absolute decrease with depth, fractional decrease with depth. The same sort of formulae that we had seen for variation in height, the same formulae are now made for variation in depth. We understand this, yes or no?
Yes, sir.
And then you can note down the last point. If you compare this variation of G with depth, and if you compare this with variation of G with height for smaller heights, you will see that the variation in the value of G, the rate of decrease outside the earth, is double that of the value inside the earth. I hope you understand what I'm saying. Basically, I'm trying to compare this formula, decrease in the value of G, with the formula of decrease in the value of G with height. But remember, there I had taken height very small compared to the radius of Earth. So everywhere you were finding the factor of 2 coming, yes or no?
Yes,
But
sir.
here there is no factor of 2, therefore variation of G with height, the rate of decrease of G with height is twice as much as the variation of G with depth. Do we understand this?
Yes, sir.
Okay, great. Then we can move on. Have you noted this down,
1 minute, sir.
everyone?
1 minute, sir.
Okay. So remember these small things, because these small things make a hell lot of a difference in our eventual answers. Why it makes a hell lot of a difference? Because there could be questions which could be coming straightforward from these uh, topics, from these small things. And if you remember these small things, you would be able to solve those questions pretty quickly. And if you can do them pretty quickly, that means you can save time in the other questions where you might require to spend more time. Yes.
Done, sir.
Done, sir. Then comes this question, sir. It's a simple and a straightforward question. Weight of a body of mass m decreases by 1% when it's raised to a height h above the Earth's surface. The body is taken to a depth h in a mine. What will be the change in its weight? It's a very simple and straightforward question. I hope you can give me the answer straight away. What will be the answer for this one, my dear friends? What will be the answer for this one, my dear friends? Yes, I'm waiting. Waiting. No answers.
1 minute, sir.
Why 1 minute you need? Why do we need 1 minute? That raises doubt. Why do we need 1 minute? Yes, why do we need 1 minute?
B, sir. Sir.
Yes, why do we need 1 minute?
B, sir.
B, sir, 0.5% decrease. Everyone understands this? Yes or no? No, yes.
Yes, sir.
How did we get this?
Um, D by R.
How did we get this?
D is 2H, sir.
Yes, bacha.
D is equal to 2H. Then 2H by R into 100%.
We have already seen it. We have already seen what? That the variation in depth or variation in height is 2 times the variation in depth. Yes or no? No,
Yes,
yes.
sir. Yes, sir.
So when it is raised to a height, it goes by 1%. So when it is raised to a depth or when it's taken to a depth, it will also decrease, but it will be half of that. Yes or no? No, yes.
Yes, sir.
So you can see we have done this question pretty quickly. Well, otherwise that would have been, we would have to think, but once you understand this concept, you might not have to think. Can you move on to the next question? I'll give you 2 minutes to solve this. So here comes the next question. Question number 2 in this category. The depth d at which the value of acceleration due to gravity becomes 1 by n times the value on its surface is. I'll give you 2 minutes to solve this and get me the answer. Option B is correct. How are you supposed to get it? You just need to apply the formula. Which formula? G dash is equal to G into 1 minus
1
d
minus.
by r.
Yes, sir.
The value of G dash is given as 1 by n times.
1 by
So
N. Yes,
you
sir.
can write this as G by n will be equal to G into 1 minus d by r. From here, it is a simple calculation, and that calculation can be done, and you can get the answer straight away. Yes or no? Everyone got this? Can I raise hands that everyone got this? Okay, raise hands gives me more confidence that we are doing good. Okay, on that note, we'll move on to the next. What next? Next reason for variation of G. What is the next reason? We have seen the three reasons. Move on to the last one. And this is the most important one because normally we neglect this variation in G. What is the next one?
Latitude, sir.
Latitudinal. Sorry, did you say latitudinal? What do you mean by latitudinal? They say, what do you mean by latitudinal? You are right, but what do you mean by latitudinal degrees? I don't understand it. Yes? Tell me what is latitudinal degrees? And where did you hear this term latitudinal? It varies with it varies because of latitude. Why? That is what I want to ask. Why does it vary because of the latitude? Huh? Or where did you hear it? I'm surprised that you know it. Where did you hear it? Tell me.
Sir, due to poles.
Due to?
Poles. Poles.
Due to poles. No, we have already seen that was variation in G because of the shape of G. Because of the shape of not G, because of the shape of Earth. Yes, because of the shape of Earth, it varies. It is more at poles and less at the equators because of the shape. Because equatorial radius is more. That that is one reason because it varies. The second reason because it varies is this. Reason number D: rotation of Earth. Rotation of Earth You must understand that Earth is rotating
Hmm.
from where? West to east or east to west?
West to east. West to
Huh?
east, sir.
East to west or west to east?
West to east, sir.
Yes, Earth rotates from west to east, and that is why sun rises from the east and not from the west. Okay, so basically what happens is better. If you can see this diagram, because of rotation of Earth on its own axis, we all experience a centrifugal force. Do we understand this? Now, because of this rotation of Earth, we all have to have some centrifugal force because we have to rotate with the Earth. Now, this acceleration due to gravity or the force of gravity is always acting towards the center of Earth, which is this mg. Do we see this? Right? Now, because of this centrifugal or centripetal, whatever you call, we also require this force because we want to stay on Earth, and therefore your net acceleration due to gravity goes in this direction. This d dash goes in this direction. Do we understand this?
Yes, sir.
You understand how is this g going? And this vectorly, if I talk about vectorly, this net magnitude mg dash vectorly is equal to this vector mg plus this centrifugal force, if I want to call this a centrifugal force. Now, the centrifugal force is m omega square into r, and because of the angle between mg and fc, which is equal to minus of pi, we get this long formula, and I will show you both the formula. You can note down. From this formula, we get the actual value of g, which is not g, but it is taken as g dash. It's not g. This is how we put the values. And here we get the formula for the variation in the value of g with due to rotation of Earth. And what comes here is this latitude lambda. What comes here is this latitude lambda comes, and that is why I was surprised when you told me it varies because of latitude. This latitude comes. This lambda is the latitude at that point. This omega is the angular velocity of rotation of Earth, and this becomes a formula for your variation of g with or because of rotation of Earth. Because of rotation of Earth. Now you can see, since this lambda is your latitude, on your poles, the latitude becomes 90 degrees. And on the equator, your latitude becomes 0 degrees. So because of rotation of Earth also, G varies. And because of this factor also, G is less on equator and more on the poles. Do we understand this?
Yes, sir.
So once you put the value of lambda latitude in this equation, you will get the value of G on poles, and the value of G on poles will be coming as equal to your Gm by r square. That is why we say that the value of G 9.8 meter per second square is on poles on the surface of Earth, and that is the maximum possible value of G that we have anywhere on the planet. Do we understand this? Do we understand this?
Yes, sir.
Value of G on equator we will get by putting the value of lambda as 0. So it becomes G minus omega square R. So it will always be less than G. And what is the variation? The variation is small, but the variation is there. And the variation is this much. 0.034 meter per second square is the variation because of rotation of Earth. Do we understand this?
Yes, sir.
Now there is a very familiar question, and I will give you that question. Everyone has noted this down?
1 minute, sir.
Okay, there is a very familiar question, and I'll give you that. Something has happened. I will have to restart the thing. Things keep on happening in life. We'll have to. Have you noted down that one?
Yes, sir.
So now the question goes like this: what should be omega of Earth so that an object at equator becomes weightless? An object at equator becomes weightless. You should get your answer in terms of G and R. What is G and R? G is your acceleration due to gravity, and R is the
Is the
radius of
radius
Earth.
of
I
Earth.
will give you 2 minutes to do this. So, how do we do this? It is very simple for you to do this, right? So, on equator, what is the value of G? The value of G is G dash is G minus R omega square.
Sir.
For anything to become weightless, the value of G dash should become equal to 0.
Zero. Yes,
So
sir.
that will be equal to this, and omega will be equal to root over
G by
G
R.
by R, and that is the answer that we were looking at. Do we understand this? Yes or no?
Yes, sir.
Okay. Then, okay, we can go ahead with this. Okay. So this is what we have to understand about the acceleration due to gravity. We have covered all questions on acceleration due to gravity. Anyone has any doubts on this?
No, sir.
Okay. Now we can move on to the next heading, which was the heading for today's class. And the next heading
Gravitation
is
potential.
gravitational potential. Gravitational potential. What do you mean by gravitational potential? Yes, anyone? We have done with gravitational field, gravitational potential.
The
Yes,
done with the
gravitational potential.
the amount of work done required to bring a point at infinity to gravitational field.
Yes, that is absolutely correct. Gravitational potential. Now, gravitational potential should be actually gravitational potential difference. Gravitational potential difference is actually right, because absolute value of gravitational potential is not defined. The absolute value of gravitational potential is not defined. What is defined though is the difference in gravitational potential, or the change in gravitational potential. Now, so you must remember this. Absolute value of gravitational potential is not defined. Absolute value of gravitational potential is not defined. What is defined is the change in the value of gravitational potential. So, how do I define the change in the value of gravitational potential? If I write gravitational potential as delta V, change in the value of gravitational potential is negative of work done by gravity. Change in gravitational potential is
Negative.
negative of work done by gravity per unit mass. What do I mean by this? So, for example, if I have a point A and a point B, and I shift a mass from point A to point B, from point A to point B. So change in gravitational potential, if I call the potential of this point as A, and if I call the potential of this point as B, change in gravitational potential will be VB minus VA. That will be equal to negative of work done by gravity per unit mass. Or I can write it as negative of gravity negative of gravitational force dot dr divided by mass. Do we understand this?
Yes.
But force divided by mass becomes gravitational field, so it becomes minus g dot dr. Do we understand what I'm writing here?
Yes, sir.
The change in gravitational potential is defined. Now, do we understand this? The absolute value of gravitational potential is not defined, only change is defined. Now, instead of writing it as VB minus VA, I can multiply it by negative sign and I can write it as VA minus VB. That will be equal to work done by gravity per unit mass. Yes or no?
Yes, sir.
I can write it like this. So that will be equal to integral of G dot dr. Now, no one is going to ask you the definition of gravitational potential. So, do you understand the definition of gravitational potential from here?
Yes, sir.
Yes or no?
Yes, sir.
Okay, so you don't need to write the complicated definition. You just need to understand this. Now, to find out the absolute value, we need a reference point, right? Now, if the gravitational potential of infinity is taken as 0, your infinity is taken as your reference point. Your infinity is taken as your reference point. Then you can find out the potential of any point with respect to infinity. Yes or no?
Yes, sir.
Right? So, whenever we say if infinity potential is taken as 0, we can define the potentials of all points with respect to infinity. We understand this? Yes or no?
Yes, sir.
Okay. Now, let us Now understand what type of quantity is gravitational potential. It is a scalar quantity. Do we understand this?
Yes, sir.
Gravitational potential is a scalar quantity. What will be the SI unit? It will be joule per kg. Yes or no?
Yes, sir.
Or you can write it as meter square per second square.
Mm.
The dimensions of this will be L square T minus 2.
2.
Now, remember, and this is the difference between gravitational potential and electrostatic potential. Electrostatic potential created by a positive charge is positive, and electrostatic potential created by a negative charge is negative. Do we understand this?
Yes, sir.
But gravitational potential created by any charge,
Is
oh, not
negative.
charge, any mass, gravitational potential created by any mass is always negative. Will you remember this?
Yes, sir.
Gravitational potential created by any mass is always negative. Gravitational potential created by any mass is always negative. There is no mass in this universe which can produce a positive gravitational potential. This is how it is different as compared to your electrostatic potential. You understand this?
Yes, sir.
Okay. Gravitational potential at infinity is taken as zero. This is the highest value of gravitational potential because we are talking in negative sense. So zero is the most value, the maximum possible value of gravitational potential. Do we understand this?
Yes, sir.
Okay. Have you noted it down?
Done, sir.
Now that takes us to the next heading, gravitational potential due to a point mass. What is the gravitational potential due to a point mass? So if you have a point mass m and you have a point p at a distance of r from this, what is the gravitational potential due to this point mass? Now if I talk about the gravitational field, oops, why I'm drawing it there? I'm still in electrostatics. If I draw the gravitational field will be going like this, yes or no?
Yes, sir.
And the value of gravitational field is Gm by r square, yes or no? The value of gravitational potential is minus
G M
Gm
by R.
by r. Gravitational potential due to a point mass is minus Gm by r. Gravitational potential due to a point mass is minus Gm by r. Now remember, gravitational potential is a scalar quantity. If you have more than one, if you have more than one point mass, how will you find out the gravitational potential due to more than one point mass? How do you find out the gravitational potential due to more than one point mass? How will you find out the gravitational potential due to more than one point mass?
We have
Hmm?
to add them all
Yes, beta?
We have to add them all.
You will have to add. Yes, it is simply the addition. Why it is simply addition? Because it is just a scalar quantity. So if you have a large number of particles like this, M1, M2, creating a potential at point P, the net potential will be the sum of potential created by the individual particles. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note it down. Okay. Then what you can do is you can solve this question. Let's see how many of you can do this. So you have a diagram. Question number one. 2 point masses separated by distance L. Then there is a point Q midway between them. And there is a point P, the distance equilateral triangle it is. So distance is given as L. Can you see this? Yes or no? You can understand the diagram? Yes or no?
Yes, sir.
You can understand the diagram? Yes or no?
Yes, sir.
This is the bigger version of the diagram if you don't understand this. The first question is you have to find the potential of point P and Q due to the 2 point masses. Question number one. Then the next question is find out the work done by external agent in bringing a unit mass from P to Q. The third question is also find the work done by gravitational force. I'll give you 2 minutes. Think about this and give me the answer. So how are we supposed to do this? How do we find the potential of point
Sir,
Q? First,
potential at P is minus 2 gm by L.
potential at P is minus 2
G
gm by L.
L
Agreed. What is the
and
potential at point Q?
minus gm by L.
Minus gm by L. How?
Or else minus 4 gm by L.
Minus 4 gm by L. Okay, now you can mass, there is a unit mass. So the mass is 1 kg. So unit mass is 1 kg. Now you have to find out the work done by gravity. Let us first find the work done by gravity. How will you find the work done by gravity in bringing a unit mass from P to Q? So work done by gravity in moving the mass from P to Q. Gravity. How will you find it out? Now, if you divide it by the mass, that will be equal to potential difference between P and Q. Yes or no?
Yes, sir.
So basically what you got to do is you just need to multiply this by the unit mass. So work done by gravity in moving the unit mass will be Vp minus Vq multiplied by m. Do we understand this?
Yes, sir.
From P to Q, if you want to move a charge, the work done by gravity will be Vp minus Vq into m. So you can just subtract them, get the answer and stay happy. So what will be the work done? It
2
will be 2
gm square
times
by L.
Gm by L. Mass is unit, so it is 1 kg. So mass is 1 unit. Do we understand this?
Yes, sir.
Now, what is the work done by this external agent? So remember this formula. Work done in moving this point charge, point mass from P to Q by an external agent is negative of this. So it is final potential VQ minus initial potential VP multiplied by M. But this equation is only valid when change in kinetic energy is zero. So we move it very, very slowly. So whenever this question comes, this is how you have to solve it. So the work done by the external agent would now become minus 2 times Gm by L. Do we understand this? So remember this because this same thing is going to come in the chapter on gravitation, my dear friends.
Electricity.
Do we understand this?
Yes, sir.
Okay. Then comes this question. The next question. I had forgotten the number, so I'll call it question number 4. And we had done the brother of this question. Now this is the cousin brother of the same question. An infinite number of point masses, each of mass m, are kept at 1, 2, 4, 8, 16, 32, and so on. We had found out the gravitational field. Now is the time to find out gravitational potential, and you have 2 minutes to do it. Well, just to help you out, this is the diagram that you had to draw if you had to draw a diagram. Same diagram we had done for gravitational field.
Yes, sir.
What is the answer? So it will find you. It will form an infinite series. Yes or no?
Yes, sir.
Potential P will be V1 plus V2 plus V3 and so on up till infinity. Yes or no? So your V will become minus Gm comes out. 1 plus 1 by 2 plus 1 by 4 and so on till infinity. This is an infinite GP. Yes or no?
Yes, sir.
So V becomes minus Gm.
-1.
What is the value of this infinite GP, bacha? Don't know the value of infinite GP? Huh?
C,
1
sir.
upon 1 minus
-4
half.
GM.
It should not have taken so much of time. Minus 2 GM would be the answer, beta.
Yes,
And
sir.
that is exactly where we wanted the answer and what was the answer. Do we understand this or this is gone above saying bye bye? Sir,
We
I'm
got
going
it,
bye
sir.
bye. Bye bye.
No, sir, we got it. Done, sir.
Okay, then, sir. Then let's see, sir. This question is coming again. Let's see if you remember this. These are the this is the way questions are framed in a JEE. Let's see if you can do this one. Question number 5. Two bodies of mass m and capital M are placed at a distance d apart. The gravitational potential at a position where the gravitational field due to them is zero is how much? 2 minutes you have to show your talents. So what is the answer for this one?
D,
And it
sir.
is D. It is D. Remember, we had done this question where we had seen two
Yes, sir.
masses and we had seen where the gravitational field is zero. You have to remember this. So where is the gravitational field zero? If I find the distance from the body of mass capital M, the value of x that we had seen was root over capital M upon root over capital M plus root over small m. Yes or no?
Yes, sir.
Into D. And the distance from the smaller mass, if I call this as x1, if I call this as x2, that will be root over small m divided by root over capital M plus root over small m times
Small
t.
m into
So now if I have called the potential, total potential as V, it will
L
be V1 plus
V1
V2.
plus V2
V1 will be minus G
minus
into capital
G
M by
plus
x1 minus G into small m
small
by
m by x2.
x2. You just have to put the values, get the answer, and stay happy. Well done. That means you remember it. Good. That is a good thing that you remember it. Now we must understand uh, point mass is not the only type of mass that might come to us. So we must now understand potential due to various types of bodies, and we will only deal with a couple of bodies which are going to come in the exam. The rest of the bodies we will deal with in the chapter on gravitation. So the first body is ring. We had seen the gravitational field due to a ring. Now we see the gravitational potential due to a ring. At any point on the axis of the ring, the gravitational potential is minus gm upon root over a square plus r square. At the center, you put the value of r, the distance x, whatever, as 0. the potential becomes minus gm by a. Remember, this potential does not depend on the distribution of mass.
Hmm.
Now, no matter how the mass is distributed, if the total mass is m, the potential do not depend on distributed mass. No matter if you distribute the mass uniformly, then this will be the answer. If you distribute the mass non-uniformly, also the answer will remain same. Do we understand this?
Yes, sir.
Because it only depends on the mass. It is a scalar quantity. It does not depend on the distribution of mass, because I have seen questions where the mass was given slightly different, not uniformly distributed, and then they have asked what is the potential at any point on the axis of the ring. The next one is a hollow sphere or a spherical shell. Hollow sphere, spherical shell, the for the G greater than R, it is same as the formula of point charge. For distance on the surface, it is same as point mass. And remember, inside the shell, the potential is not zero. Electric field is zero. Sorry, gravitational field is zero, but potential is not zero. So we will write those important points also once we are done with this. So when gravitational field is zero, that does not mean that the gravitational potential is zero. It means that the potential is constant, and therefore you have this graph of this gravitational potential. Do we understand this graph that has been drawn? Yes or no? No, yes.
Yes, sir.
I'll give you 2 minutes to draw it. Once you're done, please let me know. Then comes the case of sphere, earth, any solid sphere. At any point outside, the gravitational potential is same as that of a point mass. On the surface, gravitational potential is also same of that of a point mass, but inside the gravitational potential is somewhat different. It varies like this. And you must remember this formula. The way I remember this formula, it's not like this, but I hope you can remember this. I remember this formula in this way: minus gm by 2r cube into 3r square minus small r square. This is the way I remember this. What you got to understand here is potential at the center is minimum minus 3 by 2 gm by r, and it is 3 by 2 times the potential on the surface. Here potential changes because there is gravitational field. I hope you understand what I'm saying. Yes or no? No, yes.
Yes, sir.
Okay, I'll give you 2 minutes to note this down. Also draw the graph. Are you drawing the graph as well?
Yes, sir.
So what we have done up till now is to understand the gravitational potential due to different types of object. Now, what we can do is I can obviously make a question on this, and let me make a question on this so that you are able to understand what type of questions are going to come. Let me just make one question or two question on it. Okay, I can make that question. Okay. So the question goes like this: there is a ring of mass m and radius a, and this ring is fixed, it cannot move. There is a point P and there is a small mass kept at this point, and this small mass is at rest. What will happen to this small mass if I leave it? What will happen to this small mass if I leave it? Will it remain there? Will it remain there?
So once repeat the question.
Yes, sir, or no, sir?
So once repeat the question, sir.
The question is written on the board. What do you see on the board? Ring of mass capital M, which is fixed. Let us call the radius as root 3 times. Uh, let me not make it on the ring. Let me not make it on the ring. Let me make it on the sphere. That is better. So let me change the question. So I'm going to change the question for you. Oops, what has happened? What is happening? Okay. So let us say I have this sphere, or you can treat this as Earth. This is a planet of mass m and radius r. This planet m and there is a small mass kept at infinity at rest. And this is a Earth or planet, a big planet. What will happen to that small mass? This big planet does not move, it remains at rest. What will happen to that small mass? The name of this chapter is Gravitation. So please understand that. There is a planet, big mass, and then there is a small mass very far away from it. What will happen to this small mass?
It will get attracted, sir.
It will get attracted to, it was at rest, it will start moving. Let us say it moves along this line. What will happen? It will strike the planet with some velocity v, yes or no?
Yes, sir.
You have to find out the velocity v with which this particle strikes the planet. Find out the velocity with which the particle strikes the planet. The particle is at a large distance from the planet. It's free to move. With what velocity will it strike the planet? I'll give you 2 minutes to do this. If I can do this, that's very great. How are we supposed to do this?
Gravitational force is equal to centripetal force
Centripetal force.
plus
It is moving in a circular path.
2h.
Okay. So that point is infinity. This point is A. What I'm going to do here is apply work energy theorem from infinity to A. What does work energy theorem state? Work energy theorem states that work done
Work done is equal to change in
by all forces is equal to change in kinetic energy.
kinetic energy. Yes, sir.
Here there is only one force which is acting. So work done from infinity to A by gravity, that must be equal to change in kinetic energy. Final kinetic energy is half mv square. Initial kinetic energy is 0. Yes or no?
Yes, sir.
What is the work done from infinity to A by gravity? That will be m, mass which is moving, multiplied by v at infinity minus v at point A. Yes or no?
Yes, sir.
That will be equal to half mv square. What is the potential at infinity?
0.
What is the potential at point A? Who is creating potential at point A? Earth, or this mass is creating potential. So how much is the potential at point A?
Gm by r.
minus Gm by R, and
minus
minus of
GM.
that minus Gm by R becomes G into capital M by R is equal to half V square. That means your V becomes root over 2 Gm by R. Do we understand this?
Yes, sir.
Yes or no?
Yes, sir.
This is how you should have done this anyways. Let us say that there is a tunnel dug exactly at the point where it hits. So what will happen now? It will go towards the center of this planet. Yes or no?
Yes, sir.
The next question is, with what velocity it hits the center of the planet? VO. With what velocity it hits the center of the planet? It's going to keep on moving. With what velocity will it hit the center of the planet? I have a tunnel dug. With what velocity it hits the center of the planet?
Root over GM by R, sir.
Yes?
Root over GM by R.
How did you get it?
Escape velocity.
Yeah?
Orbital velocity, sir.
Yes?
Orbital velocity, sir.
What is orbital velocity? What do you understand by orbital velocity? I'll give you 2 minutes to solve it. Can you solve it or shall I do it?
No, sir. We will do.
No, there is no time left. So, anyways, with what velocity it is going to hit the center of the planet? I will now apply work energy theorem from infinity to point O. Work done by all forces is equal to change in kinetic energy. The only force is gravity. From infinity to point O, the work done by gravity shall be equal to change in kinetic energy. What is the work done by gravity from infinity to O? We multiply mass m, potential at infinity minus potential at point O.
Yes.
That should be equal to half
Half
mv square. M से m कट गया, gone. What is the potential at infinity? What is the potential at
potential at
infinity?
infinity is 0, sir.
What is the potential on the center of the planet?
Minus V naught is equal to
What is the potential at the center of the planet?
minus V square by 2.
Huh?
Okay. Minus GM by R,
Just
sir.
told you 5 minutes ago. You can't remember it 5 minutes afterwards. How will you remember it 5 months from now? Anyways, no point of me going about the same issue. You will not remember it. I knew it. So the potential at the center of the sphere is minus 3 by 2 gm by r. That is the only reason I had given you this question. But as always, you have not surprised me. I knew that you will not remember, and you have not remembered nothing new in it. So minus of minus will become plus. So it will be 3 by 2 g capital M by R is equal to half V square. 1/2 also goes away. So your V at the center of the planet with which it hits is 3 G M by R. That is the answer that I was looking at. This question was done only for one reason and one reason only, that you understand what is the potential at the center of the
Center of
sphere.
yes, sir.
Anyways, I hope that you will remember it.
Sure,
So
sir.
this is how you can use this concept of potential to find the work done from infinity to A. We'll do the same question in a different way, not in a different way, same way, but put in a different way in the next class. So see you in the next class, and I hope that I will be able to wind up this potential difference and potential energy by the end of this next class. That would be the intention, so that we can wrap up your gravitation by Sunday. I think you will have a class on Sunday, and that would be a longer class. So I'm hoping that I wrap up your gravitation on Sunday. That is my
Yes, sir.
objective, so that we'll work towards achieving that. Once we are done with this, and there is only two or three things left, which I think can be done in that class. So take care, and God bless you all. Please remember things that we do better.
Sure,
Everything I'm
sir.
not everything that is possible I'm telling you, but it will only make sense when you remember it.
Yes,
Otherwise, it
sir.
is all going down the drain, waste. Anyways, I hope it's just could not remember it. Not a problem. I hope you'll remember it now.
We'll
Take care.
remember,
God
sir.
bless you all. Bye bye.
Thank you, sir. Bye.